Okay, so now we're gonna move on to chapter 8, and chapter 8 is viscous pipe flow. And so here we consider viscous flow in pipes and ducts. And so here when I say pipe, that implies a circular cross section. And the duct implies a non-circular cross section. Like for example, in your home HVAC system, the ductwork in your HVAC tends to be rectangular, and so that's called a duct. And the analysis that we're going to learn in this chapter is important for, and this is important for analyzing long H2O, oil, gas, etc. pipelines. You can use it to analyze hydraulic systems. You can use it to analyze HVAC systems. And water lines, pumping requirements, etc. Okay, so now if we want to determine the pumping requirement to move liquid down a pipe, so to determine means a flow going down a pipe. So let's just consider a pipe, and we have the pipe cross section here and a pressure gauge and then another pressure gauge here. Okay, and the flow is going from left to right at some velocity v, and we'll call this P1, P2, and they're separated by a distance L. Okay, well, in reality, P1 will be greater than P2 because of pressure drop. And that's true even if the cross-sectional area at station 1 is the same as the cross-sectional area at station 2. And so, and that delta P, or that pressure drop, is caused by viscous losses at the wall. So the delta P caused by viscous effects or viscous shear stress at the walls. And we'll get into that later on. And now, many practical systems don't have just straight sections of pipe, but they can have like fittings and elbows and valves and things like that. So we also need to consider those. So if we have a little tank here, and we're going to suck up some water in a goofy piping system, and we have an inlet here, and another tank here, an outlet here, and a valve here. Okay, and a pump. Okay, well, all of these components, these elbows, and the valve, all of these components here also add losses to the flow. That is, the flow has to be turned as it goes through the elbow. That's going to introduce a delta P across the elbow. There's a delta P across a valve, especially if it's partially open. There's a delta P associated with the inlet, because the streamlines will have to go down, around, and up, and there's going to be a lot of viscous losses for that. And so we need to, so when we analyze a practical piping system, we need to account for those losses too. And so there are losses at the pipe components. And those are called minor losses. And we'll discuss those later. And the delta P at straight sections of the pipe, just due to fluid friction at the wall, that's and those are called major losses. And we'll get into why they're called major and minor losses. Okay, and so we will discuss these things in detail and learn how to analyze them for practical systems. And so now the general characteristics of a pipe flow. Okay, and so if we consider a tank with a pipe attached to it. Oops, I don't know why my thing did that, but it did. So we have a tank with a pipe attached to it. And, well, initially, in ideal circumstances, the velocity profile as the flow goes into the pipe from the tank, the velocity profile will be fairly uniform. But as the flow moves downstream into the pipe, the flow velocity will change, and eventually, if we go far enough downstream, the flow velocity will be essentially constant. Okay, and so this region here, where the velocity profile is changing, is called the entrance region. And what's causing that is, if you recall, we had the no slip condition. And the no slip condition was that the velocity vector in the tangential direction is equal to 0, or v is equal to 0 at the walls. Okay, if you're assuming that the flow cannot go through the wall. So that's just saying that the velocity right at the walls of the pipe has to be 0. Okay, so that means even with this flat profile here, there's a very tiny sliver of fluid, say right here, that is actually not moving. And as the flow goes downstream, that region of slow fluid is actually going to grow, and the growth of that slower moving fluid is going to look something like this. And you'll have a similar thing coming up from the bottom. Okay, and this region in here is called a boundary layer region, and we're going to discuss that more in chapter 9. And this is affected by viscosity. Okay, and I'll call the boundary layer BL, and the BLs grow with distance. Okay, and so eventually these boundary layers, which mark the region of fluid that is affected by viscosity from the wall, and the region of fluid that is not affected by viscosity, these eventually grow, and the boundary layer from the top eventually merges from the boundary layer from the bottom, and at that point, the velocity profile it doesn't change anymore, and so it does not depend on. So here the velocity profile is the same here as it is here, and so this region is called the fully developed region. Okay, and in the fully developed region, the velocity profile is not equal to a function of x, and I'm defining x as the distance from the tank. Okay, and so in the fully developed region, this velocity profile is not changing as a function of distance down the tube. It is the same. And so in the entrance region of the pipe flow, is where the fluid has felt the presence of the wall. Okay, and in the fully developed, I'll call that FD for short, a region, the velocity profile is not equal to a function of x. And so that implies that partial x of u, v, or w is equal to 0. Okay? But just because the velocity profile is invariant with distance, partial p, partial x is not equal to 0. Okay, so please keep that in mind, that even though the velocity profile in the fully developed region here is constant with respect to distance, that is, it's not changing anymore, the pressure is changing. Okay, and so in this class, we focus on steady, incompressible, fully developed pipe flow. Okay, and relaxing any of those assumptions adds a lot of challenge to the calculation. Okay, and so in this class, again, we're going to focus on steady, incompressible, fully developed flow in pipes and ducts. Okay, and now because it's steady, we can show, because it's steady, you can steady or incompressible, you can show that at any section of the pipe, I'm going to scroll up again, sorry about that we could draw a control volume, say here and here, and we can show that the integral, that conservation of mass, basically states that the integral over any cross-sectional area along the pipe, v dot n hat dA, equals a constant. Okay, and this constant is the volumetric flow rate. So basically, this is saying that Q is constant along a pipe. And you guys should intuitively know this from your homework problem. You've actually used this quite a bit. But in this chapter, I'm not going to make you derive this relationship all the time. You guys should be pros at that by now. Okay? And then Q will equal to the average velocity, and I'm going to get into that later, times the cross-sectional area. So if you know the volumetric flow rate, you can use conservation of mass to assert that at any section of the pipe, no matter if there is a change in the area, that Q is the same. So if the flow is going in here and out there, that Q is the same here as it is here, as it is here, as it is here. Okay, and if you need the average velocity profile, or the average velocity, you can just simply take Q and divide it by the local cross-sectional area, as you guys have done all kinds of times in class. And so, so how do we know if the flow is fully developed or not? If the flow is fully developed. Okay, well, there are various criteria, and I'm not going to get into how they're derived. For laminar flow, it comes from something called boundary layer theory, which we're not going to get into in this class. But for a laminar flow, which for laminar flow in a pipe, that basically means the streamlines are basically going in straight horizontal lines along the pipe. And so that is, the fluid is just moving in various layers or laminae. And so that's what laminar flow means. And streamlines are flat. Okay, and the L over D for fully developed in laminar flow is approximately 0.06 times the Reynolds number based on diameter. And recall that this is the Reynolds number based on diameter. Okay, and RED equals rho U average, which is the average velocity at any station, times the diameter over the viscosity. Or in a form that we use from time to time, it'll be the average velocity times the diameter over the kinematic viscosity, because nu equals mu over rho. Okay, and so we will use those two quite readily. And so essentially, since we are assuming fully developed flow for this class, that the analysis we are going to use is really inaccurate if you have a very short, stubby little pipe. So say we're draining a tank, and we have a very short, stubby little pipe here, where L over D is much, much less than 0.06 RED. It is not fully developed, and you cannot use, in such a situation, you cannot use the analysis techniques that we're learning in this class, and you have to. It becomes much more complicated because you need to account for those boundary layers and things like that that are going to be formed, that are going to be developing but not fully merging, and things like that, and they're going to dominate the characteristics of the flow, and it's going to be complicated. Okay, and so and then for turbulent flow, and we're going to discuss what I mean by turbulent flow here in a little bit, or in another lecture probably. So, but for turbulent flow, the L over D for fully developed flow is equal to 4.4 RED to the 1/6 power. Okay? So, you can see that for laminar flow, the distance along a tube where the flow becomes fully developed scales with RED raised to the 1 power, whereas for turbulent flow it scales with roughly to the 1/6 power. And so for a turbulent flow, which is most practical flows, for a turbulent flow, the distance required to achieve a fully developed flow is typically much shorter than for a laminar flow in the same diameter tubing. And now for turbulent flow, and we're going to discuss this in a bit more detail in a subsequent lecture, these streamlines are no longer flat lines. And so what they look like are little wiggly, chaotic lines, and they sometimes cross each other, and they're going all over the place. Okay, so essentially for a turbulent flow, the flow is very chaotic. It is technically always unsteady, but there is a mean velocity that is steady that you can use to basically analyze things. And another characteristic of turbulent flow is that the velocity profile, even when fully developed, is very flat. Okay, and we will use that. We will use that empirical result to our advantage down the road. Okay. And so now that now I'm going to end this video. In the next lecture, I'm going to discuss pressure drop for laminar flow.